Can you all hear me okay?
Yes.
Okay. So I have several demos to do today too. From now on, I'll probably have several demos in the lectures because of the topics we're covering. And so I'm going to be I'm going to have to disconnect my microphone every once in a while. Just be aware of it. If you have a hard time hearing me, just let me know. Okay. Just some announcements. Chapter 26 homework is due on the 16th. I think I'm going to try this week, if I can, to re-upload all the assignments onto Canvas so it shows the right dates. Well, today I've been in one meeting after another, so I was planning on doing that today, but I haven't had time. Some of you folks have emailed me regarding missing lab equipment. That's not good that you guys got some stuff missing. I need to know what's missing. So when you got the equipment, you should have gotten a list of equipment in your with your kit. Please go through your kit. Don't wait till the day before the lab is due, or a couple of days before the lab is due, to check what's in your kit and what's missing. I need to know what's missing. It's going to be especially important for the new lab we start on Thursday called the Ohm's Law Lab. Okay. There's several of you don't have the bag with wires and a proto board in it, and you guys need that because otherwise you can't do the lab. Okay. And so one way we can get you that stuff is like we can meet you on campus. Like tomorrow, I will be on campus in the afternoon. Okay, I am for a meeting. But if you need any equipment, please let me know. And so for me to get on campus, I have to actually plan that at least a day ahead of time because I have to get permissions to get on campus. I just can't walk on the campus right now because of the COVID stuff. So I do need lead time. Okay, if you need something. Otherwise, if it's something I have here at home, I can basically, meet you on. I can meet you in the parking lot and swap equipment with you. I'll give you my stuff, and you give and for example, if your multimeter goes bad, I can give you mine. Okay, but if I need to get something from inside the building, I need special permission to get in. So I need lead time for that. Okay, just so you're aware, please go through and check out your missing lab equipment. Exam 2 will be graded before Thursday. I'm on the last problem. Basically, I've graded all the problems except the cube problem. And in fact, I've graded the cube problem in a couple people. So there's actually a couple exams that I finished. It doesn't look good, let's just say that, okay? Especially compared to compared to last semester. Okay. One thing that is really bothersome to me when I grade an exam is if, I get a document that's way too big. Okay, so when I try to read your exam and on my screen, and I can only see half your page at a time because it's so big. We need to fix that. In fact, I have to take off points for that because I said in the syllabus you have to fix that because, we did the cam scanner assignment. Okay. Those of you who made the giant prints, copies of the exam, if you download that file and you try to print it out, you'll see what I mean. Even if I download it, some of them, if I download them, I have to look at them in the PDF form at 30%. Then I can see it. Canvas doesn't allow me to do that. Well, what I've done in the past is, what I have done is, if I've warned you on previous, I haven't taken off any points, but if I've warned you on previous assignments, make it smaller, and you haven't, then I would take off points. So I do give you a chance. Okay?
Hey, Professor.
Yeah.
For the chapter 26 homework, is that the one that says it's due today, or is that a different one?
No, the one that's due today is chapter 27. That's homework 5.
And it's supposed to be due today, just to clarify.
Correct. Yeah. That one's due
Okay,
today.
cool. Thank you.
The chapter 20, that's why I'm specifying it by chapter instead of by homework assignment. And again, I had to go out of order because we needed to do multimeter quiz.
I have a question. Is it possible for you to like instead of naming the homeworks like homework 9 or homework whatever, can you name them based on the chapter? Because sometimes it's kind of confusing and on which chapter exactly is a homework on. Because I know in lecture like before we were doing like chapter 25 and then 7 and
Well, the rest of them after this one, they're going to be in order.
Okay, all right.
Okay,
Sounds
so it's only been that way just because I had to make some slight changes. But
okay.
the rest of it's
Thank-
fine. So the exam is not curved, the whole course is curved. Okay. All right, I covered the entire course for this reason, because sometimes, well, for two reasons. I mean, really, because writing the exam for an online class is way different than writing the exam for a class that's on ground, and the college will not let us have the class on ground. So I have to write the exams differently. If this was a class where it was just multiple choice tests, that wouldn't be a problem. Okay, because I can use a test bank with hundreds of questions for you guys to use. Okay, so yeah, it's the entire course is curved. All right, so basically what I'm going to do is look at your final grade and curve that. I will on this test. What I'll do is give you a comparison. I will show you based on my curve what the grades would have looked like on the exam and what your current overall grade looks like. And that's something you guys can do too, because all you got to do is actually no, you guys can't do it. All I got to do is calculate the average and just go by whatever the standard deviation is. So if you're within, if you're 1.5 standard deviations above the mean, that's an A. Okay. Does that make sense? Okay, so I will do that. You know, I might not have it for every exam, but I want to do it for this one at least. I didn't do it for the first one because it was the first exam. And after the first exam, all the scores are, if you look at all the averages, it's pretty high. You don't want to see that curve. Okay? That curve would not have been in people's favor if everybody's bunched together above 80%. Okay, but now it's going to be a little bit different. Okay. I did, typically on this test, I will say this. What happens when the class is on ground, you know, when we're face to face, typically on the exam, I get a huge bunch of scores in this low 60s, in the low 60 percentile range, and then maybe one score above 90. When I did this last semester, I had a huge bunch of scores in the 50s and maybe one score above 90. I think there was one, because I taught 2 sections last semester. I think I had one person in one class got above a 90, then the other class, the highest was like 88 or something. That's typically what happens. It's just hard to get 100 on the first test, but then a bunch of people are just bunched either in the 50s or in the 60s, depending on whether class is face-to-face or not. That's not going to be the case this time. I mean, I do have a score that's over 90, but then I have a bunch of scores below 50, a whole lot. That's worrisome. Well, I don't know I don't know the actual final score, but I can tell I'm going to have a lot of scores below 50. Okay, and I've never, ever had that happen. Okay. So that's a concern, and we can talk about that on Thursday. All right, because I want to grade that last problem. Okay. So my objective is to discuss chapter 26 on capacitance. And one more thing, lab videos. I tried to upload the lab videos the other day, and somehow they didn't get uploaded. I was having internet issues, so that could have been the problem. So they are on Confer Zoom, except the one on Confer Zoom, and I keep forgetting, I forgot to pin myself in here. The one on Confer Zoom kind of shows everybody's names and stuff on them. The one on YouTube does not. Let me pin myself. Okay. But anyway, for the time being, take a look at those. I will upload them right after I upload this lecture. Okay, so hopefully it goes okay. And it takes a long time because these files are like 10 gigabytes each. Okay, at least on my, because I'm using a Mac. The Mac saves the movies as a MOV file, which are huge. All right, a couple people asked me, and I didn't have time to answer the question in office hours, so I'm doing it now. Problem 8, homework problem number 8 on the homework. And I drew a picture for problem number 8, because I think there might have been some confusion as to what problem 8 was saying. So in part A, basically you have a copper wire and a platinum wire connected one after the other. These are in series. So basically you have two resistors in series. Okay, so basically what happens is the resistance of this wire plus the resistance of this wire gives you a total resistance. Just imagine if you had one single wire, okay? So this is the case for 8A, and in 8B, the two wires are connected in parallel. Okay, and so you know the resistance of this one because you're given the voltage and the current through it. Okay, you're given the voltage and the current through it, so R of the copper is going to be delta V over I, but that's also given as the resistivity of copper, that's the chemical symbol for copper, times L over A. Okay, so you know R for this one. Now for the platinum, the resistivity of platinum is the resistivity of platinum. I forget the chemical symbol, times L over A. Now the L and the A are the same for both. So their resistance, the resistance of the platinum wire as compared to the copper wire, since they're the same length and area, are only going to be different by the factor of the resistivity of the two objects or materials. Does that make sense? Okay. And then for the second part, these two are in parallel, so they both have the same voltage across them. Okay? They both have the same voltage across them, and the problem asks for the total current. So the total current is going to be the total current through the copper plus the total current through the platinum. Does that make sense?
Professor?
Yes.
For the first part, so because they are connected to
In series? I'm sorry, I lost you.
together,
I keep losing. Yeah, you add them, right? I mean, if you had a single wire, right? If you had a single single wire connected like this, right? One twice as long as the copper wire, then the total resistance will be twice that. So you're adding them.
So what we would do for the parallel case?
For the parallel case, well, if you know the resistance, of the two, then you just calculate the current through one plus the current through the other, and add them together.
I read it somewhere that you would have to do 1 over R equals 1 over R1 plus 1 over R2 to get the resistance.
That's if you want. Yeah. Now you're getting a chapter ahead. You don't have to do that for this problem right now, because you know the total current that's going to go through here is going to be the current through the platinum wire plus the current through the copper wire. Isn't that true?
Yes.
So then all you got to do is sum the two currents, and that's it.
By individually considering their resistances.
Correct. And
Okay.
yeah, in chapter 27, we'll talk about what happens when you combine these two. But I don't want to do that yet.
Okay,
Professor?
okay, yeah.
Okay? I'm trying to avoid that because I don't want to use the methods of a next chapter to solve this problem.
Hey, Professor.
Yes.
For me, it says that part A is still asking for the current through those wires.
Right. So you need to find these two, though, right?
Well, okay, so I did this problem and I cannot seem to get the right answer, but I found the ratio that you're talking about, and then I just did the voltage over the sum of their resistances.
So I don't know if this will help you, Damien, but I kept getting it wrong when I was being more specific with the resistivity of platinum, when I was saying that it was 10.6 times 10 to the negative 8, but I got it right when I did that it's 11 times 10 to the negative 8. And it's such a small difference that it fixed it for me.
Ah, okay, I'll try that then.
I tried to use the values from the book.
Yeah, and that's what the book lists. That's why I just said in the chat to use the table in the book on page 814.
Yeah.
Because when I was using specific values that I found online, they were a little too precise.
Yeah. I try to be consistent and use the ones, because I made that problem up. I used the ones from the book. Okay, so
that's just my fault then. I was using 10.6 instead of 11.
Okay. Yeah, and in fact, before class, I looked at it. There was another source that said 10.5. So.
Professor?
Yes.
For the parallel case.
Okay. You keep cutting out. So I guess go ahead and type it. Yeah, because they have different resistances, right? They have the same voltage across them, but different resistances, so they have to be different, right?
Yes. Okay.
All right. So I hope that's sufficient for that problem. By the way, when you do homework problems from the textbooks that require you to use a particular value, always use the value from the book. Okay? Because it might be slightly off and you might get the wrong answer. Whether you're doing a problem in this course or in 215, for example, because in 215, for example, when you talk about, especially beginning course, when you do thermodynamics, you talk about heat transfer, the values you use have to be those from the book. Otherwise, if you use a reference from online, it could give you it could be specific to a different type of material. For example, there's different grades of aluminum. There's different grades of steel, etc. And so a website online would probably be more specific The textbook version is very, very general, okay? So you see less sig figs. Okay, so let's get into chapter 26. And so far we've talked about charges that are not moving. And in chapter 26, we're pretty much going to do the same thing, although you're going to see some instances where charges are moving. But our goal is to move towards the cases where charges are moving. What happens when you have charges that are moving? And so that's chapters 27 and 28. All right. But an important topic involves how do we store energy, and that's pretty much this chapter. Okay. And we're going to learn about a new component in the circuit called a capacitor. And they have a lot of applications. Let me look at these questions in here. Yes, that is correct. The electric potential decreases in the direction of current. So the one question in the chat, that's correct, Raftej. The electric potential always decreases. We always talk about potential drop in the circuit. Okay.
Yeah, I was just asking that because I think I asked this before and you said that it does not matter in which direction we are talking about. It was something like that in the direction of the positive charges, the potential.
Yeah, so whether you have I guess I wasn't completely my thought when I said what I said this morning was that whether you have a negative particle moving to the left or a positive particle moving to the right, I is the same. That the current is moving in the direction of the electric field, right? Because J is sigma times E, correct?
Yes.
So if this is to the right, then that has to be to the right. Right, J is I over A, right? Essentially. Okay, so if this is to the right, that has to be to the right.
Okay.
Okay, and so the electric potential then so the current goes in the direction of decreasing decreasing V, sorry.
Okay.
So, let's talk about capacitance. Oops. If you do an experiment, you can show that the charge on a single isolated conductor will depend on the size and shape of the conductor and the electrical potential. Oops. Hold on just 1 second. So what we want to do is define a quantity that relates the potential to the amount of charge, and really the potential difference, to the amount of charge and the amount of energy stored by the field. And we're going to define this thing called capacitance. And I should mention, you'll hear the phrase that capacitors store charge. You got to be careful with that. Okay? When people say capacitors store charge, we're talking about the charge in one plate. Because basically what happens is when you have a capacitor, one plate stores a positive charge, the other plate stores a negative charge, and equal and opposite. The sum of the two equals 0. Okay? Okay, for some reason my keyboard is not working. So we're going to define the capacitance as the ratio of the magnitude of the charge on the conductor divided by the magnitude of the potential difference. We're going to define this to be a positive number. We're also going to say that if we have a pair of oppositely charged conductors, we're going to call that a capacitor. Okay, if we have a pair of oppositely charged conductors, we'll call it a capacitor. Now, capacitance doesn't only need, we can calculate capacitance for a system of multiple conductors, but we're not going to get into that here. Okay, just realize that. But for us, we're going to look at basically a pair of oppositely charged conductors. They're going to form something called a capacitor because they're going to store energy. I don't like saying they're going to store charge, although people say that. So
Do
what
they have
happens?
this? Oh,
I'm sorry, go ahead.
do they have the same magnitude of charge? So it's just like always positive Q and negative Q?
Yes, like in the figure you see there.
Yeah, cool.
Yeah, and so when you add them together, what do you get? Right, you get 0, right? So some people object to the fact when you say they store charge because the total charge is 0, but really what they're implying is they put charge on the charge. They put charge Q on the capacitor on each of the plates. One's Q, one's minus Q. Does that make sense?
Professor?
Yes.
If like suppose one of the plates had a slightly different dimension, would still the charge be same?
Can we assume that the plates are big?
Okay.
Because otherwise there's edge effects, right? I mean, in reality, no. But I mean, if the plates are big, what'll happen? Let's say you have one plate like this, and then another plate like this. All the charge will essentially be here. Does that make sense? We can almost ignore that. Obviously, there's edge effects we're ignoring. Okay, we're going to ignore that part.
Okay.
Okay. In fact,
And isn't it a delta V that gets stored in the capacitor?
well, delta V is not something. There's a potential difference across the plate, but you don't store electric potential. You store energy, right?
Oh, okay.
Right. You store energy. You don't store delta V. And we say you store charge because you put charge on each plate. They're oppositely charged, though. The sum equals 0. And people will still say that. Okay. But really, they store energy.
Okay.
Okay.
Professor?
Yes.
So if like you connect a battery to that to the two plates which you have drawn on the board, then would the charge be distributed such that there is equal charge on that portion of the bigger plate as like the same as the one on the bottom?
Yes. If you hook up a battery to it,
Okay.
yeah, they'll be.
Mm-hmm.
Yeah, you'll have the same. Well, one will be positive, one will be negative, but their magnitudes will be the same.
Okay.
Okay. Okay, so when you connect the battery, you're gonna set up an electric field, and it's gonna cause charge to flow between the battery and the plate until the wire, the field in the wire is 0. Okay. Charge will flow to the plate until, because this is why I talked about the charge sharing problem. Charge will flow onto the plate until the potential of the plate equals the potential of the wire equals the potential of the battery. We say that about both. We say that about both sides of the capacitor. And so what you end up with is a positively charged plate that you see there and a negatively charged plate also. So since by experiment delta V is proportional to Q, we write that Q is some constant times delta V. And C is our capacitance. So we define the capacitance as the magnitude of Q over the magnitude of V. It's always written as a positive number. They're coulombs per volt or coulombs squared per joule. It's a farad. And a farad is a very large unit. If you wanted to make a 1 farad capacitor and use in between the two plates air, it would probably be big as maybe room 101 in Sewell. Okay. If you put a material in between the plates, you can actually make a 1 farad capacitor. It's much smaller. In fact, if you put special materials in between the plates, you can make the capacitor very small. So let me show you a couple of examples of capacitors. Okay. So I'm gonna hold a couple of them up. Here is an example of a capacitor. And in fact, let me change cameras so I can show this up close. I will unplug my microphone. So here's a, oops, I just ripped my capacitor. This is a capacitor we took apart. Okay? So basically, it's two sheets that you see here, and in between is a material, it's like paper. That brown stuff that you see in between is the paper in between the conductors. And it's rolled around, it just rolled up into a long cylinder. This is actually a capacitor that was taken apart. Okay? And these are designed to store energy. Let me get another one. A couple more. This one is, let's see, a 65 microfarad capacitor. And you can charge it up to 2,000 volts. If this thing discharges through your body, it'll kill you. And so normally what we do is we short the two terminals on it. So this is a very dangerous device. Okay, so they can be extremely dangerous. This one is extremely dangerous. Your air conditioners have a big starting capacitor. Your cars have them too. Okay, so basically, you can use these to deliver a large amount of energy in a small period of time. So an example is you watch the medical shows and someone goes into cardiac arrest. What do they usually do?
So is this kind of like a solenoid?
Yeah, I mean, a solenoid could do a similar thing, but its behavior is different. Your car does have a solenoid too, right?
Yeah.
Yeah. So, but going back to the application, if somebody goes in cardiac arrest in a medical show, what do they do to them?
Shock them.
They shock them, right? Yeah, they shock them. And so that device stores. They have a big capacitor, stores a lot of energy in it. It's like 300 joules. You do not want to dump that into you, okay? Because it's a lot of energy, okay. So yeah, inductors. So an inductor coil. We're going to talk about those later this semester. They have a different behavior, and they require changing currents for them to work. Yeah, for some reason I couldn't think of the word defibrillator. Thank you, Kai. So yeah, we'll talk about those also. Where else do capacitors work? On your keyboard. Every single key on your keyboard has a capacitor on it. They're also used to set time. So for example, if you look at your windshield wipers, the intermittent wipers, that's just a capacitor and a resistor circuit. Okay, because when you use those two in combination, it slows down how much the resistor slows down how much the capacitor charges. And if you know the value of the resistor, you know the value of capacitance, you will actually know how fast the capacitor will charge up. So you can use it for timing.
Did you mean to say that it slows down or it reduces the amount of charge it contains, or does it just reduce how long it takes to get to the maximum charge?
Well, if you increase the resistance, it increases the amount of time it takes to get to maximum charge. Ideally, the picture I showed you before with the two plates. Hold on a second. And when you connect the battery and the plates get charged, I mean that's a very short period of time. For all intents and purposes, that's instantaneous that those plates get charged. But now once you start putting the resistor, then it takes much longer. Because resistors oppose flow of charge. So although you can put the same amount of charge in the plate, it just takes longer. Does that make sense?
Professor?
Yes.
So the reason we put something in between the capacitor is it because the air can get ionized?
That's one reason. Another reason is, and I'll talk about this next time. Another reason is you can actually store more energy. It'll actually increase the capacitance when you put a dielectric in between the plates. So what I was showing you was, let me go back to the camera. This is 65 microfarads, okay? And I'm not sure what's in here. Some of these have oil in them, but I don't think this one does. If I get time, I will use this one. This capacitor has a material called aerogel in it. That's a 1 farad capacitor, but it's limited to 6 volts. So this is this is an actual 1 farad capacitor. Okay. So basically, the material you put in between the plates can increase the capacitance. It'll increase the voltage you can apply across the plates of the capacitor, and it also provides physical stability to the system. Okay. All right. So let me go back to the PowerPoints. These are all good questions. I did forget to show you one. I'll show you one more capacitor in a minute. So the unit of capacitance are in farads, but usually we rate them in picofarads, microfarads. So you'll hear the term picofarad, microfarad. You'll also hear, you rarely hear nanofarad. So picofarad is 10 to the minus 12 farads. Microfarad is 10 to the minus 6 farads. Okay. So let's talk about, and let's derive some equations. I don't want to do it just by going through the PowerPoint slides. I want to derive an expression for the capacitance, really of various systems. You can actually derive the equation for the capacitance of various systems. And I'm hoping my keyboard works. So let's say we have 2 plates. And we connect it to a battery. A cell, whatever. Let's say this ends up being positively charged. This ends up being negatively charged. This will have plus Q minus Q. And then the charge density, these charge densities are going to be equal but opposite. And we know that the electric field between the plates the total electric field between the plates, so I'm just going to do the magnitude, is sigma over epsilon naught, because both of them produce a field that points to the right. Okay. What is the potential difference between these two plates? Well, I can measure it. I mean, I know what it is because it's delta V. But I also know that, well, what do we know that's special about the electric field between these two plates?
It's constant, assuming they're big.
Yeah, it's uniform, right? So the electric field is uniform. So that means that V varies linearly. Okay, the V varies linear. In other words, delta V, the magnitude of delta V is E times D, where D is this separation between the plates. And so this is going to be equal to sigma over epsilon naught times D. But sigma is the charge per unit area, isn't it? This is just Q over A. And so what I want to do is calculate Q, the magnitude of Q, over delta V. And when I do that, with the algebra, I'm going to get epsilon naught A over D. So the larger I make the plate, the more charge I can put on it. The further away they are from each other, the less charge I can put on it. That's what this says. So this is the capacitance for parallel plates. Like the other day, the last problem I did in class, I did the capacitance, and I didn't say it directly, but I did the capacitance for the concentric cylinders. You folks remember that?
Mm-hmm.
Yeah. So I already did that problem. It's in your notes here. So I did that problem. So I'm going to skip that one here. Okay. So I did it the other day. I mean, I didn't say it explicitly, but for parallel plates, what you got to do is you got to figure out the expression for delta V, and then a Q over delta V. That's it. So one of the things you want to practice on, because this will help you get better in learning the material from the previous unit, is learning how to calculate C for different geometries. The book has examples. Okay. So we're going to use this a lot, okay? So for a parallel plate capacitor, so basically what I did was I found the expression for delta V from my knowledge of the electric field, and then I took Q over delta V. Okay. So the other day we did the concentric cylinders. And we calculated actually C over L because they're infinitely long. That's for the concentric cylinders. So you should go through this calculation again. I did this last problem I did in the lecture in the last unit. I calculated delta V, and then I said, let's calculate lambda over delta V. And that's the capacitance between the length. Okay? These are concentric. If they're separated by a long distance, where this is D, and little d is the diameter, then we can write C over L is 1 over K natural log of big D minus little d divided by D. And D is the diameter, not the diameter, the radius. Cylinders. So these are concentric, these are separated by D. So you try to derive these. Okay, you should try to derive these. And they're important. This particular one is very important when you have concentric cylinders. And I said, well, why? Why would it be important? If you're measuring small signals, if you're somebody who's electrical engineer measuring small signals, this capacitance becomes important. Maybe I should demonstrate that to you. Let me do a couple of demonstrations involving capacitors. Okay. Yeah, D is the, let me double check. D is the radius, sorry. This is a standard problem, they use D for it. All right, so I want to do a demonstration. With capacitors. So I have here. Can you guys see that okay? I could bring it up closer.
Yeah.
Sorry for all the sounds. Okay. So what I have here, it's weird because my image is backwards. On the,
It's a little too close.
It's too close? Okay.
Right there.
Okay, that's good. Okay, great. So this is the capacitor. This is just a parallel plate capacitor. This is what you would use if you were on campus. You would be doing this experiment. Okay, so first thing I'm going to do is I'm going to charge this up. Okay, and I'm going to charge this up a little bit differently. Then I'm going to take it apart and I'm going to use a meter to measure the capacitance. So this is called a Wimshurst generator. I don't want to use a Van de Graaff because I'll blow out all my electronics. My Zoom meeting would be over. Although this thing can store a lot of charge, so I actually have to be careful. Okay, but I'm going to run it in a mode that's safe. So this is a Wimshurst, and charges by induction, and there's these two jars here. They're called Leyden jars. I can use them to store more energy. Maybe I'll show you that when I'm done, how much energy these things store. But what I want to do is, I have this connected to the capacitor, and then I have the capacitor connected to this guy. This is an electroscope. So when I spin this, can you see the electroscope deflecting?
Yes.
So what I'm going to do is bring the parallel plates in. What do you notice the electroscope? Does the deflection change? Is the deflection going down?
Yes.
Yeah.
So what's happening? I'm going to bring it back. What's happening? I bring it in, the deflection decreases. So where's the charge going? These two are connected to each other, right?
It's pretty much just pushing and pulling the positive charge, right?
Yeah, the charge is going between these two. This is just a sort, I'm treating this like a battery. And I don't have these connected on purpose because if I did, all the charge would go into the big jars at the bottom. So yeah, I'm just pushing and pulling charge between these two. So when I push these in, D decreases and makes the capacitance bigger. All the charge on here goes to here. All the charge on the electroscope goes to the capacitor. When I increase the separation and make D bigger, then all the charge that's on the capacitor goes back to the electroscope because this can store energy. It might be, Chase. I'd have to take a look at it. Does everyone understand that? So you can clearly see that if I decrease the distance between the plates, the capacitance increases. I can store more energy. It takes it away from this guy. And to make it more obvious, let me discharge everything. Did you hear the tick? Did you hear that tick sound?
Yeah.
Or not? I heard it. Well, let me just show you a little bit about how much energy this thing can store. Since I have it, let me move it back though. I don't want it to be close, that close to the computer. Do you hear that?
Yeah.
Yes.
Okay, let me try one more thing now. I'm gonna take these levers and bring them down. And by the way, when that happens, when the air ionizes, I can smell the ozone being produced. So now I brought these levers down so these things get charged first. So these will charge up first before it discharges. Hopefully it works. Yeah, my monitor just shut off. I hope I didn't kill it. Oh, it's back. Do you saw that one? So that almost messed up my monitor. If I would have gotten zapped with that, it probably would have knocked me out. Okay, so let me make another measurement with the capacitor. Because this is a lab we do on campus. Actually, you do it. So I have a device that measures capacitance. Your multimeters do the same thing. Okay. I'm going to set this on 2 nanofarad scale. I don't know if you can see it very well. That's probably too far away. I might have, that's going to be too hard. Anyway, you might have to just believe me. Sorry. Okay. Not the same as doing demos in the classroom. Let me do this right. And I need to know if you can see. You guys see that or not?
Yeah.
You see it? Okay, I don't know why it's really negative. Okay. You guys can see that, right? Now I'm going to bring the plates closer and closer together so you can see the capacitance increase. So if I make it closer and closer together, you can see capacitance increase so I can store more energy. If I bring them back further apart. And just to show you that we are capacitance and the wires are, I'm going to see if I can bring the wires closer together. Somehow. I'm trying to bring them really as close together as I can without touching them. Because if I touch them, well, let me just show you what happens when I touch them. I'm a capacitor too. And these conductors are capacitors too, so if I make them closer and closer together, which I'm failing to do, if these get closer and closer together, you'll actually affect the capacitance of the system. If you get them really far apart, you'll get a different value as opposed to when they're close together. So these wires actually form a capacitor. So when you're doing a measurement, when the capacitance is low, you have to have these wires far apart. You cannot touch anything. You see what happens when you touch things. Okay, so you're a capacitor too. I don't know if you folks have watched the videos I put on the modules that guy called Electro Room. He talks about this when he talks about electrical safety. That you're a capacitor too. And so AC, one of the reasons why AC hurts you more is because your body will pass AC. Okay. Yeah, he almost kills himself with a lot of videos. He does that on purpose to show you. Talk about electrical safety. Okay. Let's get this out of the way, so now my demo's out of the way, so I'm tripping. If I get to it, I'll have one more demo later. Okay. Let me reconnect my microphone. I'm going to continue with my discussion. I can hear me better. Oh, so a question. What would happen if two plates of a capacitor touch together? The capacitor will discharge. See, and see that that's a good question. I do a demo. Where I use, believe it or not, a much larger version of this. Okay, I use a much larger version of this in class. There's two of them. And I charge them up to about 2,000 volts. And I do what you suggested, Rob Tej. I just short them. It's very loud. The energy gets dumped through a wire. It's very loud. No, I won't. In fact, what I do is I usually turn off the power supply, and then I short them. So yeah, the power supply is okay, because the energy will be dumped through the conductor that's being shorted. What you don't want to do is have a high voltage power supply and turn it off real quick. So you get like a 2,000 or 3,000 volt power supply. You don't want to turn it off real quick. In fact, engineers are smart enough to know that. And so what engineers do is they put a resistor and a capacitor in series, so that if you do that, the energy will discharge through the capacitor. And so it's almost impossible for you to just turn things off real quick with a high voltage power supply. So they think of those things. So suppose we charge parallel plate capacitor with a battery. And this helps us to better understand, again, the stuff from the previous unit. Okay, that's why I love to ask these questions. So let's say we charge a capacitor. Because what I'm going to do with what I say about this example is true in general with any capacitors of any shape in this example. So let's say we have two parallel plates. I charge them. Okay. And it's connected to the battery still. So let's keep it connected to the battery. And let's let D increase. So we let D increase. What happens to E? Tell me what happens to the electric field.
Well, if it's uniform, nothing, right?
Okay, so I have one person saying it decreases. So why do you say it decreases?
Wait. Oh, because it's being divided by D. So like the bigger D is, then the smaller D is. Oh, it doesn't?
Wait, but so you're looking at this, right?
Yeah.
So what happens to this?
Well, that stays the same.
So V stays the same. So delta V stays the same because it's connected to the battery.
Oh, I thought you were saying what happens to E if D increases.
No, you're right. But in order for us to see what your answer was, we have to look at this, right? If this stays the same and this gets bigger, right? What happens to E?
It gets smaller.
Smaller. You were right. I was just trying to get, the explanation.
Why does that not line up with like the value of E we solve for when we're looking at the plates? Because isn't it uniform?
Yeah, it's still uniform, but remember, I'm separating the plates, right?
Oh, so we're just saying that the strength of the electric field decreases, but it's still uniform wherever you are.
Correct. Yeah.
Gotcha.
So what happens to the capacitance?
Professor?
Yes.
But like, we said that E is equal.
I keep cutting out.
To
Yes, you're right. E is sigma over epsilon naught. You're correct. But before you ask the next question, how do you know sigma? Why does sigma not change? Why should it stay constant? It's connected to the battery still. Right? How do you know the charge is the same? What's the restriction if it's connected to the battery to keeping the charge the same? So here's the thing. Isn't this true? What happens to the capacitance?
It also gets smaller.
It gets smaller, yeah, it decreases. And now the question is, what happens to Q? It decreases. This is why I ask these questions, because these are good thought. These are very thought-provoking questions. Right? Okay, so if I make D bigger, this has to get smaller. It means charge has to go back into the battery. Now let me change the question. Because I think some of you guys were answering this question. Give me a second. Let's remove the battery. Same question again.
Professor?
Yeah.
What is the expression that relates capacitance to charge?
Oh, okay. I got rid of that one, huh? All right, Q over delta V is C, right? That's how we defined it.
Right, yeah, thank you.
Okay. So, and again, this is always defined as positive. So I should, and we always drop it, but really you should write it like this. But we always drop it because we assume we're going to take the positive value of these, okay? Okay, so I disconnected the battery. I'll let D increase. Now, what happened to C? Let's do that one. It's still charged. I just took away the battery, so it's still charged. What happens to C? It still decreases, right? Anybody disagree with me? What happens to Q?
Doesn't it stay the same?
Yeah, it ain't going to go anywhere, right? It can't go anywhere. So what happens to sigma? The charge density, that stays the same. And so now what do we say about the electric field?
It has to be constant, right?
Stays the same, yes.
Sorry, the same.
What about delta V?
Stays the same, then delta V would too, right?
This stays the same, this increases.
Oh,
So wouldn't delta V increase then?
Yeah, increases. So delta V increases. Remember, this is the amount of joules per coulomb in your system. So that means that the energy between the plates really increases. Where's that energy coming from? Well, it comes from the person pulling the plates apart because you're doing work on the system. If I pull the plates apart, I'm doing work on the system. I'm storing more energy into the system. That's right, I'm storing more electrical potential energy into the system by pulling the plates apart. Those, when you did the electrophorus, if you look at the spark at larger distances above the wax, or not the wax, but the styrofoam or the saran wrap you used, you probably would have seen a bigger spark as you increase the distance. That's because you did work on the system. Now that part, when we do that part in class, when you guys do that part, when that part of the lab is done face-to-face, it's much more clear to see. Okay, so we're okay on this? I like these questions because it helps us to think about everything, all the dynamics in here. Okay? The two cases are different. Okay, so normally what I do is I talk about capacitors of concentric cylinders. Oh, why does V increase again? Well, take a look at this equation. If this stays the same, which you've established, and this gets bigger, shouldn't this get bigger? Okay. So this capacitance problem, calculation capacitance problem, which I did the other day, that's this one. Except that this would be a D and this would be a C. It doesn't matter. Okay, I did that one already, so I don't want to go through it again. Save time. You can watch the video from the previous lecture that I had, and you can see me do this calculation. Okay, you should go through and know how to do this calculation. Okay,
Professor?
Yes.
If delta V increases, then does the potential energy of the system increase too?
Yes, that's what I was saying. Right,
Got
if you make delta V increase, you store more energy in the system.
Right.
That's what happens with electrophorus. When you separate the two oppositely charged conductors, you'll get a bigger spark. Let's say when you touch it, or let's say when you touch it with your finger.
Right, yeah. Thank you.
Okay. So this particular problem that I kind of did in class the other day, and I'm not going to do it now, is important when you're looking at small signals. So if you're an electrical engineer, you need to understand this problem. Okay. We can calculate the capacitor of concentric spheres. We can calculate the capacitors of spheres that are a distance apart. Okay. All you got to do is write an equation for delta V and then take Q over delta V and you're done. You should know how to do those. Those are common problems.
The book was talking about how even like a single charged sphere has capacitance.
Yes.
That was confusing.
Yeah, and in fact, I will if I have time, I will calculate that capacitance when we talk about energy. It'll probably be the next lecture. But yeah, we can calculate, you can calculate the capacitance of a single capacitor. And here's the thing. This is how you can model it. I know, because we defined it for two oppositely charged conductors, right?
Could you do it the same way you do electric potential, where you send one of them off to infinity? Yes.
So I'm going to draw two spheres. We want to find the capacitance of this one, right? I'm going to draw a second one. Well, actually, I'm not going to send the second sphere to infinity, but I'm going to make its radius infinitely big. So this radius is infinite. So V equals 0. Okay? So that's how I can imagine it. But I'm going to show you a different technique to calculate this. You can do this, right? Because look, if you have this sphere, V is K Q over R, right, on the surface. Isn't that true? And V at infinity is 0, so I'm just putting V there. So Q over V is what? So I'm done. And by doing it, I'm assuming that the other capacitors and the other spheres at infinity. So that's it. But I'm going to show you how to do it a different way. In physics, we try to figure out more than one way to solve problems because mathematically it might allow us to do it one way, where in the other way you might not be able to do it. So now what I want to do is talk about connecting capacitors in a circuit. Suppose I take two capacitors. And again, they're used to store energy, they're used for timing. Your calculators have capacitors in them, your random access memory a capacitor. If you take your calculator, do a calculation, turn it off, and then turn it back on, you'll probably still see the results of your previous calculation because of the capacitance hasn't discharged yet. So I'm going to try to do all my capacitor examples before I end the class today. I know I'm running a little bit late, but I kind of want to do them. And I don't even know what time it is. Hold on a second. Okay, I got some time. So suppose I take two capacitors, C1, C2. I don't care what shape they are. They can be this funky shape. Okay. Hold on a second. They can be this funky shape one, or the parallel plate one I showed you, or something like this. This is a capacitor also. I'll talk about this one next time. Whatever shape it is, I don't care. Let's just know what the value is of the capacitance, C1 and C2, okay? So I connect these to a battery. So what happens? So it's the electrons that can move around. So what happens is charge will flow onto this plate until, and this happens in a very short period of time, but I'm slowing this down. Charge will flow until the potential on this plate equals this potential. But in the meantime, as that's happening, what's going to happen here? When this plate sees this negative charge, what's going to happen to this plate? Well,
Positive charge is going to get attracted to that.
Yeah, the electrons are going to run away, right? Whatever electrons are here are going to run away, leaving positive charge here. And of course, same thing is going to happen here. The same amount of charge that goes on to here is going to be here. The same amount of charge that the same amount of electrons, or let me rephrase that. If this loses 24 electrons, then this is going to gain 24 positive charges. Okay, and the same thing here. So what can you say about the charge on each one of the plates? Let's say that this positive charge and this negative charge, they're the same, aren't they? And this charge and this charge, they have to be the same. And that has to be true because where else could the charge go? It can't go anywhere else. So both capacitors charge is conserved. Both capacitors have to have the same charge. Meaning this plate and this plate has the same Q and this plate have the same Q. Okay?
Well, isn't that assuming that they have the same capacitance?
No, that's not true. Right? Because remember, charge has to be conserved, right? Because otherwise, where's it going to go? Where's the missing charge go? There's no other path for the electrons to go, right?
Well, it's just when I was working on the homework, I was getting help from Tyler, and he said, let me try and find it. It was for number 5. There was one capacitor with C and the other with 3C, and he said the delta V was the same for both of them, but not the Q.
That's a different circuit because those are in parallel. These are not in parallel.
Oh, so it's only when they're right next to each other?
Yeah, that's a different circuit.
Oh, okay.
Okay, so that's actually the next case. So both of the Qs the Qs are the same. Okay. So that means that delta V's, the potential differences are different because of this equation. That means that delta V1 is going to be Q over C1, and delta V2 is Q over C2. If the Q's are the same, this has to be true. But when we talk about circuits, this potential difference plus this potential difference has to be equal to this. So if, let's say this is at 3 volts and this is at 0 volts, this point's at 3 volts, this point's at 0 volts, this is somewhere in between, we'll call X. But this difference plus this difference still has to be 3 volts. So delta V1 plus delta V2 has to be equal to delta V, meaning Q over C1 plus Q over C2 has to be equal to delta V. But suppose I wanted to replace these two with a single capacitor that does the same job. I want to replace these two with a single capacitor that does the same job. Well, that single capacitor is still going to have the same voltage across it. So you're going to have Q over C effective. So then I have Q over C effective equals Q over C1 plus Q over C2. The Q's cancel, and you get the value of the effective, the capacitance that replaces these two and still gives you the same charge is this. That's how capacitors add in series. It's going to be very confusing because when we do resistors, the equation for resistors is going to look like this when they're in parallel. So When capacitors are connected in series, they add in reciprocal. Okay? Be careful with that because people make mistakes on that. It's the same, right? Because I'm replacing these two with a single one. It's still connected across the same battery, right? That's how I get this relationship, right? That's what gives me that relationship. Now let's do the parallel case. Actually, I think the parallel case is easier. Because each capacitor, and you saw this with your light bulbs in the multimeter quiz, each capacitor is going to have the same voltage across it. So each capacitor has the same delta V. Let me draw delta V, sorry. So each capacitor has the same delta V.
Professor,
Yes.
your capacitors are
I'm sorry?
still in series.
Oh, geez.
Your capacitors are still
Sorry.
in series.
Yeah. I'm not thinking because I'm in a hurry. Thank you.
Hey, Professor, just to clarify, the problem number 5 on the homework, I think the capacitors actually are drawn in series with a resistor between them.
Let me get to that later, okay?
Okay.
Everybody always has a hard time with that. And it bugs me too. Isn't it true that these have the same delta V across them? And so then the Q on each one is going to be different. So Q1 has to be equal to C1 delta V and Q2 equals C2 delta V. And the total charge provided by the battery is whatever is on here plus whatever is on here. And what I want to do is replace those two with a single capacitor that does the same job. C effective or C equivalent, however you want to call it. So you look at this equation, the delta V's are the same, the delta V's cancel. And this is for parallel. Okay? So those are equations for series and parallel. And I have this in your notes, the whole thing derived. So again, as a review, for capacitors in series, if you have a whole bunch of them in series, they add as reciprocals. And if you add them in parallel, they add just numerically. And all the C's are positive numbers. They are defined to be positive number. Okay? So what I want to do is this particular problem. And I think I will do this. So I will do this problem to finish off. And I just would like to do my one demo. I actually have two demos, but I think I'll just do one of them because I forgot to do my one demo for current. But I want to do my other demo just because I have it set up. Okay, so this problem is kind of completely solved. I chose numbers that are easy for us to work with, so I hope I'm not going too fast. So here's a circuit. What do you say about that one? They're neither series nor parallel, right? You have a whole bunch of capacitors. So what do I want to do? I want to replace all that mess of capacitors with a single one that does the same job, so that the battery delivers the same amount of charge to the equivalent capacitor. How do I approach this problem?
Do you start with the two on the right in series, and then once you find one for both of those, you do that one and the one on the left in parallel, and then you do the last two in series?
Correct. That's the exact way I want to do it. That's perfect.
Oh, cool.
So what you want to do is you just simplify the easy stuff, right? So the two 10s are in series, right? And the equation for series, I'll go back to the board real quick, is 1 over C1 plus 1 over C2 equal 1 over C effective. So 1/10 plus 1/10 is 2/10. What's the reciprocal of 2/10? What's 10 over 2? It's 5, right? Okay, so I take those two, combine them, and I redraw my circuit. Now I have those two microfarad capacitors. They're in parallel. They add. What's 5 plus 5? 10. I redraw it. Okay, now the hard part is to combine the 10 and the 2.5. If you do it on your calculator, 1 over 2.5 plus 1 over 10, then take the reciprocal of that, you get 2. And so this last picture shows you the equivalent the equivalent capacitance of your circuit. So that's fine. Okay, that's good. But I can figure out more information though. Because what's the voltage across that 2 microfarad capacitor? It's 10 volts.
10.
So how many coulombs is on that capacitor?
20.
20. Okay, so let's go backwards. So I have 20 microcoulombs on this 2 microfarad capacitor. That's 10 volts. This 2 microfarad capacitor replaced a 2.5 and a 10 microfarad capacitor. Since these two are in series, and we said that when they're in series the charge is the same, then both of them have to have 20 microfarads. Oops. If I take 20 microfarads and divide by 2.5, that'll give me the voltage, because remember the equation we have on the board, on the left board, Q equals CV, then V, or delta V, is Q over C. So 20 microfarads over 2.5 microcoulombs gives me 8 volts. This 10 microfarad capacitor has 20 microcoulombs. 20 divided by 10 is 2. Okay? No, they're in series, right? They're in series. They're not in parallel. They have to have the same charge on them. That's right, charge is conserved, so they both have to have 20. Right. The 20 microcoulombs is what's delivered by the battery. No, it's not. Only if I separate them. If I separate the two, then they end up being 20, but that's not the case. I'll come back to this, Ratej. I can come back to this. Let's keep tracing backwards. So let me go back again. That 10 replaced two 5s. Those two 5s are going to have the same 2 volts across them. Okay. So these are going to have the same 2 volts across them, and then these will have 10 microfarads. They're in parallel. This 5 microfarad capacitor really replaced two 10 microfarad capacitors. They're going to have the same charge on them. The voltage will be split in half. Away. That's it. Rakesh, let me get back to your question. Let's think about how the capacitor gets two in series get charged. Okay? So I connect these. I connect it to a battery. This gets a negative charge on it. Okay. Okay, so let me go back. You're talking about this one, Chase? This is what Ravtaj is questioning too. You're talking about this one? So let me go back to when I derived the equation for capacitors in series. Isn't it true that when I connect this, electrons go to here, right? And then this becomes positively charged because the electrons from here move to here. None of this comes from the battery, does it? Nothing here gets charged from nothing comes from the battery. Isn't that true? What happens in between here does not come from the battery. Only here. So they're both going to have the same charge on them. Does that make sense? What's in between here does not come from the battery. Only what's out here comes from the battery. Well, they said, I mean, you can think of it this way, the charge separates. One capacitor separates the charge on the other one, right? Because isn't it true that when the negative charge comes from the battery here, the negative charge on this plate has to run away, right? Okay, so that doesn't come from the battery. That just comes from the fact that these move from here to here. But what comes from the battery is just this and this. That's it. Okay? Now, if I separate them, if I physically separate them, that's different. Then I will have two capacitors with separate charge. Then I have done the work to separate them.
Does the leftmost plate become positively charged because when you turn the battery on, it sends its electrons to the terminal?
Correct. Whatever electrons are here go down here.
Okay, thank you.
Sure. Are we okay with that? Okay, I want to, and I didn't get to talking about storing energy, but I like this demo. So again, let me switch camera. Let me switch microphone. Let me get rid of my microphone. Um, I don't know how many, I can't tell how many people are left.
It's a 16
16, that's pretty good actually. So, can you see this?
Yes.
Okay, so this is the capacitor. So I'm going to actually, just to show you that the capacitors store energy, I have a simple circuit with these batteries. Okay, and what I'm going to do, I'm going to store energy in the capacitor. This is a 1 farad capacitor. Okay. And I think it goes up to 5.5 volts. I only have 4.5 volts on it, so I'm not going to mess up the capacitor. Actually, you know, if you put too much voltage in the capacitor, certain ones you can pop them. Okay. All right, so now I'm going to flip this. The battery's out. I mean, these are hard to take out, but it's not connected to the battery anymore. You guys believe me? And it stays on for quite a while. It'll start getting dimmer soon. Do you notice any difference yet?
Maybe it's
But now it's getting dimmer, right?
Oh yeah, I think.
Yeah. So slowly energy will go to 0. This thing stores a pretty good amount of energy. Okay. And it'll get dimmer and dimmer and dimmer. Just gives you an idea. It's kind of like acting like a temporary battery, right? And
Is the light bulb pulling electrons from the negative side of the capacitor?
Yeah. So you let electrons flow through. This is a resistor. This is what you would call an RC. Basically a discharging circuit. Okay. So let me make it more dramatic. And I like doing this one in class. I don't know how dramatic it is when we do it. Hold on, I gotta put this back in. So I'm going to charge it up again. But this time, I'm going to send you, you know what a flash bulb is? You guys familiar with flash bulbs? No? So in the old days, the cameras in the old days would have, so you get enough light, would have a flash bulb on it. So you click the button, and this bright light would show up, right? And some of them are pretty bright. So this is an old flash bulb. And so what I'm going to do is dump the energy into the flash bulb. And it's quite a bit of energy. So here we go. Didn't work. I have another one, so I can try another one. There. You see that?
Yeah.
I still see blue, so. Okay. And it's hot. Wow, I still see blue. Okay, that was bright. So that's basically you're dumping. This has a much lower resistance, so I dump a lot of energy in a short period of time. That's why it's so bright. And this thing is hot. I mean, it's really hot, so you can't even touch it. Okay? And boy, I'm still seeing blue from that. All right. So I think the other demo I was going to do, I think I'll do it at the beginning of class next time. It was a demo on really electric current going through a wire. And I think I'll do it next time because it's already at 3. It's past 3:30. So I'll stop here. So thank you for staying with me.
Hey, Professor, do you have time for a question, or do you have to do something?
I have to